everyone, and welcome back to the series on intermediate statistics. And today we're going to be continuing our exploration of estimation theory for random variables for parameters. So today what I want to do is start off with a quick review of some of the properties that you definitely should know at this stage. So let's just quickly go through the basics. So the very first type of structure or property for estimators that you probably learned is unbiasedness. And it says that if you have an estimator, theta hat, which is a random variable, sometimes continuous, sometimes discrete, and obviously is going to have some distribution, then the expected value or the mean of that random variable should be equal to the parameter that you are trying to estimate. If the expected value of theta hat is equal to theta, then we will refer to this estimator, theta hat, as being unbiased. Obviously, not all estimators are unbiased, and therefore it's possible that an estimator, theta hat, for parameter theta, will have some associated bias, which is defined commonly as the difference between the expected value of theta hat and theta, which could be positive, negative, and in the case of 0, that would be unbiased. And if the limit as n goes to infinity of the bias of theta hat, which, keep in mind, depends on n for theta, converges to 0, or is equal to 0, then what we say is this estimator, theta hat, is asymptotically unbiased. Asymptotically unbiased. So if you don't have an unbiased estimator, sometimes an asymptotically unbiased estimator is the best you can get. And sometimes that's okay. So some of the tools that we also have for analyzing estimators, so common tools, especially when it comes to maximum likelihood estimators, the first is what we refer to as the score function. So the score function. Score function. And what is the score function? So the score function is defined as the partial derivative with respect to the parameter of the log likelihood function of theta with respect to xk. And let's just make sure we remember what little l actually is. So we, of course, start off with the likelihood function, which is the product from k is equal to 1 to n of your probability density function for x, evaluated each of the values xk. And the log likelihood function, little l of theta, is just the natural log of the likelihood function. Now, of course, not all estimators have a maximum likelihood estimator because, first off, this log likelihood function and this likelihood function need to be differentiable. If it's not differentiable, then it can't be found to be a maximum because we have to differentiate this function L with respect to theta. That would give us this score function, and then set that equal to 0. So when we set this score function equal to 0, this theta hat is our MLE estimate for theta. Right? So we have the score function, which is the derivative of our log likelihood function with respect to theta that can be used to find maximum likelihood estimators for that. And then we also have another metric which also differentiates the score function and then takes the negative expected value of it. So we represent this as in theta because there's no theta hat or xk in this expression. Keep in mind, xk is a sequence of usually independent and identically distributed random variables. So when we take the expected value of the partial derivative of n with respect to theta, which sometimes is a matrix, not necessarily a variable, then we refer to this object as the Fisher information. So Fisher information for theta. So usually the larger the sample size is, the more information you have about the parameter that you're trying to estimate. Right? So one can show one important property about the Fisher information is that n theta is equal to n times I1 theta. So if you know the amount of information that one person in your sample provides about your parameter theta, then it doesn't really matter which person from your sample you're referencing. Each of them give you the same amount of information. So in theta is just equal to n times I1 theta. That is the amount of information for the entire sample is n times the information that one element from your sample gives. Some people refer to this as the additivity property of Fisher information. And using these properties, we were able to show previously that the variance of the estimator that you're using, whether it be an MLE or an MME or any other type of estimator, is always greater than or equal to 1 plus the derivative of the bias function of theta hat for theta squared all over the Fisher information for the parameter. That is, it doesn't really matter which estimator you have for theta, the variance of that estimator is always bounded below by this object, whether it be biased or unbiased. Obviously, if it is unbiased, then this object is equal to 0, and you have 1 over the Fisher information for the entire sample. But this object on the bottom, or this lower bound, is called the Cramer-Rao lower bound, which we've already talked about in the past. So we have this property of unbiasedness, and we have these tools that are often introduced when it comes to MLEs. But these properties can be used for other estimators, not necessarily for MLEs, although they usually are in the same conversation. But they are used to create another adjective for estimators. And it says that if the variance of your estimator is equal to the Cramer-Rao lower bound, then we say that that estimator, theta hat, is efficient. So if you have an unbiased estimator and an efficient estimator, those are two great adjectives that you could have. Now, because keep in mind, every estimator is bounded below by this, and if you don't have an efficient estimator, that means your variance of that estimator is larger than this Cramer-Rao lower bound. That means there's going to be a lack of efficiency for that estimator for theta, and that can just be defined as the variance of theta hat minus the Cramer-Rao lower bound. And keep in mind, the Cramer-Rao lower bound is always less than or equal to the variance of theta hat by this theoretical property. So this lack of efficiency is always going to be a positive or 0 number. And if it's not efficient, but we take the limit as n goes to infinity of the lack of efficiency for theta hat, which keep in mind also depends on m, for theta, if this is equal to 0, then we say that this estimator, theta hat, is asymptotically efficient. So if you do not have an estimator that is efficient, sometimes asymptotically efficiency is the best adjective that you can get, right? So we have unbiasedness, asymptotically unbiasedness, efficiency, and asymptotic efficiency. So these are two categories of adjectives that we have for estimators. So the natural question is, are there other adjectives out there that we probably would want for our estimators? The answer is yes, and I will introduce you to two today. Now let us introduce the third adjective that we're going to be interested in. Suppose theta hat is some estimator for some parameter theta for which we seek to estimate. So if the distribution of theta hat converges in probability to that of theta, then we say that theta hat is a consistent estimator of theta. Some people usually get drowned in these series of complicated words, so let's state this expression mathematically. So what this means is for any real number epsilon that is small or positive, or definitely positive, then if the limit as n goes to infinity of the probability that the absolute value of theta hat, which keep in mind depends on m, minus theta, is less than epsilon. So what does that mean? So the distance between our estimator and theta is arbitrarily positive. So the probability that this is true, because keep in mind, theta hat is supposed to be close to theta. So given some epsilon, this should be highly unlikely if that theta hat is a good estimator for theta. So if this is equal to 0, then we say that this estimator, theta hat, is a consistent estimator of theta. Or you could equivalently say that the limit as n goes to infinity of the probability of this estimator, that theta hat m minus theta, is arbitrarily small. So you choose an arbitrarily small number epsilon. What is the probability that theta hat and theta is within that distance, that should be almost guaranteed. That is, the probability should be equal to 1 or get closer to 1. Then, if these things are true, then we say that theta hat is consistent for theta. Right? You also may see, in terms of notation, because some people don't like to write a lot of things, is that some people will say that theta hat m converges to theta, and some people write a little p to say that that converges in probability to theta. Now notice, because this is sometimes important clarification distance, that the limit is outside of the probability statement, and the estimator is obviously inside of the probability argument. But there is an alternative to this, and I'll define this as a second definition. If the probability of the limit as n goes to infinity of theta hat n is equal to theta. So if the probability of theta hat n is equal to theta, if the probability that the limit converges to that point 1, then we say that theta hat n is a strongly consistent estimator of theta. Right? And you could have, of course, say that the limit of theta hat does not equal to theta. The probability of that event is equal to 0. That would also be equivalent. Right? Now, is there a connection between just basic consistency, which we sometimes refer to as weak consistency, and this other definition known as strong consistency? The answer is yes, and you can probably prove this on your own. Is that if theta hat is strongly consistent for theta, then it is also weakly consistent. Weakly consistent for theta. So strong implies weak, but keep in mind weak does not imply strong. Right? And of course, if you have taken real analysis, this is sometimes analogous to uniform convergence implies pointwise convergence, but not necessarily pointwise implies uniform. But if you don't know what that means, that's perfectly okay. But this is technically linked to those types of comments. Right? So let's look at a quick example of consistency for estimators. So let's start off with a very basic distribution. Let's assume that x is associated to an exponential distribution with parameter theta. Then you should know that the expected value of x is equal to the reciprocal of lambda. And using your theories of maximum likelihood estimators, you should be able to show that the MLE estimate for lambda, which I'll abbreviate as lambda hat MLE, is equal to the reciprocal of the average of the values within that data set. And of course, you can write this as n divided by the sum of your xk, where k ranges from 1 to m. So that is our estimator for lambda. So estimator for our parameter lambda, the reciprocal of the average. Now let's recall some basic things from analysis. So recall from analysis, and you may have learned this in advanced calculus also, that if xn converges to x and g is a continuous mapping, then the limit as g of xn, as n goes to infinity, will converge to g of x. Now, this obviously looks very intuitive, but we actually use this a lot in calculus. For example, we know that the limit as x goes to infinity, or x goes to 0, of x squared is equal to 0. So from this little theorem, I guess you could say, if we have the limit as x goes to 0 of the cosine of x squared, we can pretty much ignore that function on the outside, because cosine is a continuous function. It's differentiable also. But that would be equal to the cosine of 0, which we know to be equal to 1. right? So if xn converges to x and g is continuous, then g of xn will converge to g of x. This is going to be useful for us in several of the proofs for consistency. All right? So we have this little continuous mapping theorem is what it's called. Right? So if we look at our estimator, lambda hat, which is equal to 1 over x bar. So what we can do is we can define g of x, where x is just some variable, which is 1 over x. We know that this is a continuous function on the interval 0 to infinity. Now obviously negative infinity up to 0 is perfectly fine, but keep in mind x is a exponential random variable which is supported on the positive domain, right? So this function g is continuous on every value for which the exponential random variable is going to be suited for. So therefore, if we have lambda hat, which is the MLE estimate, which is 1 over x bar, this, by the continuous mapping theorem, will converge in probability to 1 over the expected value of x bar. Why? Because we know that x bar converges to mu by the properties of the central limit theorem as n goes to infinity. And therefore, since 1 over something is a continuous function, the continuous mapping theorem says if x bar converges to mu, then 1 over x bar is going to converge to 1 over mu. So that's pretty much what we have here. So this is going to converge to 1 over lambda, because the expected value of x bar is the expected value of x, which is 1 over lambda for exponential. That's going to be equal to lambda. Therefore, lambda hat MLE converges in probability to lambda. Therefore, we can say that the MLE estimate is a consistent estimator for our parameter lambda. And that would be one way that you could prove consistency for estimators. Now notice that I didn't use any inequalities, I didn't use any arbitrarily small but positive number epsilon to prove this, but this is one way that you could go around and prove the consistency for estimators. Now I want to show you a different way that you could do it, but I need to derive a couple properties first. So let's start off by supposing that x is associated to a Bernoulli distribution with probability of success p. And if you don't remember what a Bernoulli random variable is, it's a random variable that only has two outcomes, success or failure. Probability of success is p, and the probability of failures is its complement, 1 minus p. And let's assume that our sample, set S, is equal to x1, x2, down to xk, with xk plus 1, xk plus 2, all the way down to xm. Right? So what I want to do is I want to consider, because we have one parameter in this conversation, that parameter is p. So what are you going to estimate p with? Well, you could average all of the values from 1 to n, but what I want to just focus on is to build an estimator that just looks at the average of the first k values where k is less than n. Right? So I'm going to assume that k is strictly less than n, so this is not going to work for sample sizes of size 1. So what we're going to do is we're going to define p hat k to be equal to the average, so the sum from j is equal to 1 to k, of xj. So we're assuming that this is ordered in some particular way. Right? So I leave it to you to verify that the expected value of p hat k is equal to p, so this estimator is indeed unbiased. But in case you haven't already figured out, unbiasedness is very easy to generate for estimators. So if it is unbiased, does that imply that it is consistent or efficient? The answer is, of course, definitely no. So what we can do is say, okay, well, what is the probability of the distance between p hat k and the estimator, the expected value of p hat k is for us? So if epsilon is an arbitrarily small but positive number, so we're going to assume epsilon is a real number that's arbitrarily small but positive, then this should have probability 0. So we know that by the Markov or Chebyshev inequality that this is going to be less than or equal to the variance of p hat k all divided by epsilon squared. And what is the variance of a Bernoulli random variable? Well, you should be able to prove that it's going to be p times 1 minus p all over k times epsilon squared. Notice that this object, as n goes to infinity, because this is 0 less than or equal to, the limit then goes to infinity because of the probability, so it's of course bounded by 0, of this expression, p hat k minus p greater than epsilon, is going to be less than or equal to the limit as n goes to infinity of that expression, p 1 minus p all over k epsilon squared. Right? So notice that this does not necessarily converge to 0, and we of course forced k to be less than n. Obviously notice that if we choose the entire sample, then this obviously is going to converge to 0, but since this limit does not converge to 0 in probability, therefore we can say that this estimator, p at k, is not a consistent estimator for our probability parameter p. Right? So that's kind of sad. So what is this trick in case you're not familiar with this probability bound? This is obviously referred to as the Chebyshev's inequality. So let's formally state that in case you are not familiar with it. So Chebyshev's inequality. This is very useful for proving consistency if you are familiar with some of the theoretical structures for the estimator that you're working with, whether it be exponential, normal, log normal, beta, or so on. So it says that the probability that x minus the expected value of x, which is, keep in mind, not necessarily the parameter that you want, the probability that this is greater than epsilon is always less than or equal to the variance of that estimator all over epsilon squared. And some people might call this Markov's inequality, but technically speaking, and depending on the literature that you look at, Chebyshev is a special case of Markov. But I'm not going to get caught up in the semantics here. All right? And let's consider the following theorem. If theta hat is unbiased for theta, and the variance of this estimator, theta hat, converges to 0 as n goes to infinity, then theta hat is also consistent. And this is a very, very, very beautiful theorem to use to easily prove consistency for estimators, right? So if you start off with an unbiased estimator and you know the formula for the variance of that estimator and you take the limit and it goes to 0, then you automatically have consistency. So since this is so special, let's just do a quick proof of this, or you can pause the video and see if you can prove it on your own, because it is quite useful. So by the Chebyshev's inequality, we know that the probability that theta hat compared to its expected value is less than epsilon will always be less than or equal to the variance of that estimator all over epsilon squared. So since it is unbiased, we then have the probability that the absolute value of theta hat, well, if it's unbiased, the expected value of theta hat will also be equal to theta. This will be greater than epsilon, and the probability that they are arbitrarily large will be at most the variance of theta hat, all divided by epsilon squared. Right? So if the variance converges to 0, what we have here is that this expression, the probability of theta hat minus theta greater than epsilon, less than or equal to the variance of theta hat all over epsilon squared. Keep in mind, epsilon squared is just a positive number, and the variance is going to go to 0. So if we kind of ignore that middle statement, we have that the probability converges to 0, and that obviously proves that this estimator is consistent, is weakly at least consistent. And that completes the proof. So let me just give you a quick example of how to prove consistency using this very, very efficient theorem. So example, so let's consider s squared, the sample variance, for which we know is going to be equal to sigma squared. And in case you don't remember the definition of this, this is going to be equal to 1 over m minus 1 times the sum from k is equal to 1 to n of xk minus x bar, the quantity squared. Right, so our typical sample variance. So we know that that is going to be an unbiased estimator, and in case you haven't proven this very important result, the variance of s squared will be equal to 2 sigma to the power of 4 all over m minus 1, provided that sigma is finite. So we can clearly see that this estimator is unbiased, and this expression has n on the bottom only, so this obviously goes to 0 as n goes to infinity. Therefore, the sample variance estimator is consistent, or is a consistent estimator, and also an unbiased estimator for our population variance sigma squared. And that's how you can use this very important property to prove consistency. So up to this point, we have 3 adjectives for estimators that are quite useful: unbiasedness, efficiency, consistency, and now we move on to the 4th, sufficiency. So we say that this estimator theta hat is sufficient for this parameter theta if the conditional density fxk given theta hat is independent of theta. So what exactly does this mean? So if we consider as an example the normal distribution, so let's just look at the normal distribution. So let's assume that x is associated to a normal mu sigma squared distribution. Then the probability density function for x is just going to be equal to 1 over sigma times the square root of 2 pi e to the minus 1/2 x minus mu over sigma the quantity squared. Nowhere do you see in this expression x bar is not present, right? The only random variable in this particular expression is x, right? So first thing you have to do for this theorem, or definition rather, is to find the conditional density where, for example, you have fx given x bar, where you have something with x and x bar in it, right? So obviously we can just add x bar and subtract x bar to this expression, add x bar minus x bar. Now that's xk given x bar, but again, that's not necessarily the conditional density function for x given x bar. But notice that x bar and x would be present in that expression. But for this estimator x bar to be sufficient, you cannot have the estimator in this expression mu present. That is, you shouldn't be able to see this parameter mu in that conversation. Now, obviously, in order to find conditional density functions, you would have to go back to your probability theory and remember how to do that. But there is a theorem that gives us an alternative way that is just an algebraic manipulation of the probability density function. And the theorem goes as follows. Some people will give this the name, the Fisher-Neyman theorem. And it says that theta hat is sufficient for theta if there exist functions g and h satisfying the following characteristics. First off, the likelihood function L of theta, given xk, can be decomposed. Sometimes we call this the Fisher-Neyman factorization of L. It needs to be written in terms of g, which is going to have your theta hat, and also, x1, x2, x3, and so on. It can have theta in it, and it can be multiplied by x that contains only your x's. Notice that this expression can be factored. So keep in mind, for our example, we have our mu and our x1 in the example we gave before. So here's going to be our x bar, here's going to be your mu, and here's going to be all of your other stuff in it. And just a side note, this can be the function 1. So if your original density function already had, for example, x bar, but it didn't have mu, then that would be perfectly fine if that was the conditional density function. So let's just look at a quick example for this and see how to build or prove sufficiency. So is x bar sufficient for mu for xk independent and identically distributed normal mu sigma squared? Maybe try and pause this video and see if you can prove this on your own before I give you the solution. So the very first thing, if you want to use the Neyman-Fisher factorization theorem for proving sufficiency, you need to know the likelihood function for our estimator, or our parameter mu in this case. So what are we going to have? So the likelihood function for mu, which you probably already have on hand if you already found the MLE for mu, which in this case, of course, is x bar, is going to be equal to the product from k is equal to 1 to n of 1 over sigma times the square root of 2 pi times e to the minus 1 half xk minus mu all over sigma, the quantity squared. So once you distribute that product out, you're obviously going to have 1 over sigma to the power of n, 2 pi to the power of n over 2, times e to the minus 1 half, times the sum from k is equal to 1 to m of xk minus mu over sigma, the quantity squared. Right? So what I want to do is I want to focus on this expression right here, because that's where our mu is located, and our goal is to sort of decompose that into a different expression. So what we have here, the sum from k is equal to 1 to n of xk minus mu, the quantity squared, because we can pretty much ignore that sigma squared. We're just going to factor that out anyway because our target here is mu, and we sort of need to build an x bar out of this expression because currently we do not have x bar anywhere present in the expression of the likelihood function, and our goal to prove sufficiency is to prove that we can do that in a special way. So this expression can be rewritten as the sum from k is equal to 1 to n of xk minus x bar squared plus 2 x bar minus mu times the sum from k is equal to 1 to n of xk minus x bar plus n times x bar minus mu, the quantity squared. And of course, I highly recommend you see if you can prove this expression on your own. So once you're convinced that this identity truly is held, because pretty much all I've done here is I've just added and subtracted 0 to this expression in case you can't figure it out, because this is just the expression, the sum from k is equal to 1 to n of xk minus x bar plus x bar minus mu, the quantity squared. That's my little hint for you. So once you have this expression generalized and simplified in your own, then what we have here, because notice that this is just a bunch of z-scores, so that's going to just cancel out to 0 or non-standardized z-scores. So what we have here is just the sum from k is equal to 1 to n of xk minus x bar, the quantity squared, plus n times x bar minus mu, the quantity squared. So now we can go back and rewrite our likelihood function, hopefully in our way to prove that this likelihood function can be Neyman-Fisher factorized. So therefore, the likelihood function for mu, given xk, is equal to, so we're going to have our e to the power minus 1 over 2 sigma to the power of 2. So that sigma squared is the thing that we factored out. And I just want to focus on this expression only here because that does not have our xk's in it. So that's going to be n times x bar minus mu, the quantity squared, times, and then the rest of that likelihood function. So 1 over sigma to the power of m, 2 pi to the power of n over 2, times e to the minus 1 half, sigma squared on the bottom again, and then we're going to have the sum from k is equal to 1 to n of xk minus x bar, the quantity squared. All right, so my claim is that this is a valid Fisher-Neyman factorization of this likelihood function. So let's actually see if this is the case. So my claim is that this is going to be our function g. If it is your function g, then you should only be able to see x bar, your estimator, that's going to be our theta hat, and then mu, which we do see. So there's our theta hat, there's our theta, and then we have just a bunch of numbers and functions like e and sine and natural log that comprise that function g. All right, so that's going to be our function g, so it definitely satisfies both of those properties. Now we have to look at this function h. This should only be a function of xk, right? So keep in mind x bar is a random variable. That's our parameter of focus. And this is going to be our random variables 2. And keep in mind, this function could be 1 if this g pretty much has everything we need. So if we have g x bar mu times 1, that's perfectly okay as long as you do not see xk explicitly written in this particular expression. Right? So yes, these x1, x2, x3s are in that x bar, but you do not explicitly see them here. Right? So when we look in this particular expression, you cannot see mu anywhere in this expression explicitly. Yes, I know this sigma does have a mu hiding inside of it, but it is not explicitly written, outside of cheating, of course. Right, so what you see here is you see xk here. You see our xk technically there, but as long as mu is not explicitly written in this expression, because keep in mind, we can express sigma as other estimators, for example, sigma hat. Because keep in mind, sigma is a higher order estimator compared to mu, because mu is a first order estimate and sigma is a second order estimator, or in terms of moments, I mean. So therefore, we can write sigma in terms of other parameters that are not necessarily mu, but mu cannot be mentioned in that second function. Right? So since mu is not necessarily written in this function is perfectly safe. Therefore, we have our Fisher-Neyman factorization of L, and therefore we can say that x bar is sufficient for mu. Right? So why do we care about sufficiency is, of course, the next natural question. Right? It's the question, so what? So what this statement says is, so we have our estimator x bar and a parameter mu, which are both located in this function g. So if we have our estimator here and our parameter here, then why do we even need this function h, which is part of our likelihood function? The answer is we don't. So if we consider that function, then consider the log likelihood function of that. So we can say that the log likelihood function of mu, given xk, will be just equal to this expression. So minus 1 over 2 sigma squared times the rest of that thing, n times x bar minus mu, the quantity squared, plus some stuff with no mu in it. Right? So this is going to be the natural log of g. This is going to be the natural log of h. So when we try and find, for example, the Fisher information for mu, or the maximum likelihood estimator for mu, what do we need to do? Well, we need to differentiate this function L with respect to mu. So if we take the derivative of this function with respect to mu, notice that since this does not have mu in it, it just differentiates off to 0. So it does not provide any information on our parameter from this estimator, because our estimator is just chilling here. That's all the information we need. So x bar is sufficient. It gives us sufficient enough information for us to find all the information about mu that we need. Right? So pretty much that's going to give us what we need. For example, set that equal to 0. That gives us our MLE, our maximum likelihood estimator, which of course is going to be x bar. But we don't need that h stuff. So what we can technically do is define a new likelihood function, or a log likelihood function, mu xk, and we can just define this to be equal to this h function. Right? Because if we differentiate that off, it's going to give us the same information as we did before, and nothing special is going to happen. So actually, what happens when we take the derivative of L star with respect to mu, what are we going to get? So that's going to be equal to, what is it going to be equal to? Positive n over 2 sigma squared. No 2, because the 2's cancel. So that's going to give us n over sigma squared times x bar minus mu. And it's not negative anymore because the coefficient of -1 in front of the mu. So once we set that equal to 0 and then solve for mu hat, we're going to have n over sigma squared times x bar minus mu hat is equal to 0. And therefore, mu hat will be equal to x bar, which is obviously equal to the MLE estimate for x bar. So therefore, we see that x bar is a sufficient MLE estimator for theta, in this case, mu. So I hope that this video helped you organize some of the main adjectives that you definitely should know when it comes to estimation theory, in particular, unbiasedness, efficiency, consistency, and sufficiency. Are there other adjectives out there? The answer is, of course, yes. But we'll deal with them at another time. Hope you enjoyed this video, and I'll see you around. Take care.